was how can we gain the trust of stakeholders? Transparency is important. How can we account for cultural values, for the wisdom of the social scientists and the citizens in here? How can we think about whole system or parts of system? If we think about parts of system, are we missing something really important? Because we already know about, for example, the food, energy, water nexus, and if you influence one, you influence them all. How can we combine models? And what are the interesting underpinning academic questions? So I think that the integrating decision support system has a little bit to say about some of these things. See if you agree. I've got far more slides than I can possibly get through in the time available. The reason for that is simply that they're going on the web, so they need to be understood by people who haven't actually been in the room. So I will skip through a few things quite quickly, and all you're meant to take away from that is, yes, we have considered this and we've got this right. Okay. So I'm going to talk about the integrating decision support system, which is joint work with Jim Smith and Manuele Leonelli. And then I'm going to say something about how we're starting to approach the pollinator problem from this point of view, and something about structured expert judgment. So what is food security? That's one of our application areas. It exists when everybody has enough food to eat and knows that they're going to have enough food to eat tomorrow. What is an integrating decision support system? It's trying to make coherent inference over a range of network of probabilistic models. When you do that, you need to integrate into your model building the user, the decision maker, which is typically a panel. You need to ask for them what is the purpose, what is the question they're asking, which the previous speaker was just mentioning. What are the decision space? What is the decision space? What sort of options do you have? If the problem of food security is that we don't have enough food for the people we have, culling the people is probably outside of your decision space because it would be morally objectionable. So you need to know that. You need to know what is their measure of success. What does success look like, whether that's ecosystems or whatever, and how you're going to measure that. So here's a schematic of the decision support system. You'll notice that we've got everything from food, trade and the economy, farming, demography, housing, cost of living, access to credit, socioeconomic status, and all these things combine to impact on household food security. Now the reason we've got health, rights and education down here is because actually we don't measure food security. Well, actually we're going to start measuring food security in this country at household level. Been doing it for years in the US and Canada, but we don't do that. And this was a schematic we came up with. We were working actually closely with Warwickshire County Council, and we said to them, okay, we don't measure food security. What would you expect to happen if food insecurity went up in your patch? And they said, well, we'd expect to see people doing worse on their public exams, because we know that children who are entitled to free school meals do on average worse. We would expect to see an increase in admissions to hospitals, and we can measure that through the hospital episode statistics. And we could also possibly see a rise. We shared with them the work of Laggy et al. From the Complex Systems Institute, who identified food riots throughout the world. Now, to be fair, leafy Warwickshire food riot, most unlikely, but it's a low probability, high cost event. If it did happen, it would cost them a lot of money. And you can actually measure riots, because apparently you need 12 people to make a riot, and a person of reasonable firmness needs to fear for their safety, whether or not a person of reasonable firmness is present at the time. Okay, so we have a clear definition. This is measurable. Okay. So this is the key question. This is the interesting academic question underlying this. Can we network together inputs from these disparate expert domains in such a way that we can give a decision maker a way of comparing different policies that they are considering? So we've contributed a methodology for doing this. So these are the basic assumptions. We're thinking about a panel of decision makers. The initial idea came out of the nuclear industry after Chernobyl. You get a panel of people making decisions. Should we evacuate? Should we give people iodine tablets? Should we tell them to shelter? These are our decisions, and so on. We're not looking at a combative situation here. We're thinking they all want to do the right thing. We want to get something. They know what measure of success looks like. They have an idea of what the system looks like, that kind of graphic that I was on the last slide. They'd have some general agreement that that's how the system looks. If you like, that's their mental causal model, and they have agreement about that. They also know who they would go to for bits of information about the different parts of the system. So those experts that they might go to, they might be people like the Met Office, who they have massive models, who they have runs and things like this. So actually, it's not a person they're going to, it's actually a model. situation. So we've talked about yesterday about how building a whole model can be infeasibly large, and if something changes then you've got to reparameterize and you've got to have the right data, and maybe you don't have that. So we need it to be dynamic because we're modeling a dynamic system. We need to be able to trust that the different panels of experts have expertise and that they're able to give us the information that we need. We need them to be able to pass that information to each other in such a way that we can calculate the expected utility for the decision makers. We do need it to have measures uncertainty and to passport those through in a right way. And we do need to be defensible. So you have an external auditor. Very typically in the county council you have the scrutiny committee. In government you have something similar. You might have a freedom of information request. You have to be able to say how you made that decision. So this is going to the discussion yesterday about black boxes. So we have this utility consensus, this policy consensus, and this structural consensus. So we call this the common knowledge class. So each of the processes are overseen by a panel of experts who know about the stuff. They know what their models are like. They know what the parameters of their models should be. And under each given candidate decision policy, they are able to tell you what would happen under their bit of the model, the system rather. Their models would predict if you did this, then we would see so and so, and we would be able to give you a best estimate, but also an uncertainty bound around that. Maybe it's first or second moment, something like this. I've just said that. We do need the parameter space to be a product space, so we can have separability. So these are the two things. What the future measurements might be, what about the parameters? So we've had to think about under what circumstances can this be used. So this is some of the technical stuff, which I'm going to skip through fairly quickly. So parametric union and quantitative delegation. The slides will be on the web to be seen later if we need. So we need it to be adequate. We need to be able to unambiguously calculate the utility, and we need to have confidence that we are delegating to the right experts. We want to be able to handle uncertainty, and we want each panel to be able to update their own models independently. And when we have all these things in place, we can come to our theorem, which says if we have these in place, we know we can do it. Okay, so now we can actually start working with it. So this is a bit about transparency. So there are some various overarching models that we can use for the decision support system, including things like stage trees and Bayesian networks, chain event graphs, decomposable graphs, and multi-regression dynamic models. And the idea is that if you get a set of values for your set of policies, that forms part of the discussion. The decision makers still make the decision. There may be things that you can't measure, like political acceptability, that you might also consider. So you might then make decisions. So you might have 5 policies, and you might take the one that's got the second best score because actually that's more acceptable, and actually the difference between the two isn't that big. So you calculate your scores, and you say, are we happy? And if we're happy, then we go out. We release a policy. But what about if the ordering of the decisions is kind of counterintuitive to somehow? You say, well, I wouldn't expect that to be a better one. What do you do then? Well, then you can go back to your utility and say, well, these are the attributes we wanted to optimize on. These are the ways we've weighted them. Which ones are more important than which ones? This is how it comes out with. Maybe we need to twiddle with the different importances and so on. Would that make a difference? Wouldn't it make a difference? How much difference would it make? And then people might be happy after that. But if they're not happy, then they can say, well, but why is this such a big effect? Well, then we can go back to the panel of experts that provided the inputting information and say, excuse me, Met Office, you said this. Can you explain a little bit more about why the uncertainty bands are very wide, or why this value is very high, or whatever? And so at every stage you can then unfold it and have a rationale for why you made that decision. Turning to the bees. So we do need pollinators for human food security, and we have seen a lot of worry about the pollinator abundance going down, and pests and diseases and so on. And there is a pollinator strategy being brought out because we need it. And they'd identified a lot of gaps in the knowledge and set up the pollinator initiative. So according to this, some of the reasons for decline are the loss and the fragmentation of habitat, which obviously resonates very much with this workshop here. The loss of forage, the intensification of agriculture, some of the monocultures, large swathes of the same crop which suddenly go over at the same time and put the insects into a boom bust situation. Non-native species spreading diseases, being in competition, and so on. So these are the recommendations, focusing very much on the environment, field margins and hedges and so on. Wildflowers. Coventry City Council every other year plants wildflowers right down the middle of the dual carriageway across. It's very pretty. Hopefully it does some good as well. I mean, they don't all get splattered on windscreens. So based on that, we can think, well, what is the purpose of our integrated decision support system? It's to evaluate policies affecting bees and other insect pollinators. And then what is the attribute? It's pollinator abundance, attributes and measurements, citizen science, beekeeper surveys, species distribution modelling. What are the range of decisions, interventions on beekeeper education, pest control, planting, planning, land use, pesticide bans, that kind of thing. Okay, it is difficult to measure. A lot of citizen science in there. A very interesting paper come out in PLOS One about how good citizen science is about identifying bumblebees. And there's a very interesting statistical question about actually estimating populations, because if I look at a square metre of grass and I see a bee, I know there's at least one bee. If I looked harder, I might see more. So actually human effort has to be included in that modelling process. So what do? You get a blackboard and you get some experts, right? And you start drawing out what you think is the basic idea from the papers you've read and what you know. And then you go to people who are actually experts and you say, this is my model, what's wrong with it? And they tell you. So this is very interesting. So you're actually getting people, and I was able to get a large number of people to either on telephone interviews or to come and actually talk to me about the model we got and tell me what was missing. And we came to some consensus. Fortunately, there wasn't actually a huge amount of disagreement about what should be in the model and how things are. So we got some consensus on that. So that's the qualitative stuff. So what we're going to do now, parameterize the model, elicit the quantities that are not in the literature, and test and refine it. So this was the model that ended up. You'll see that it's a dynamic Bayesian network because we've got some loops here, which then so there'll be 2 or 3 copies of this unfolded in time because honeybee abundance this year affects it next year, etc., etc. So what we didn't have is some of the numbers. We can get the data for the marginals, but for the conditionals it was much more difficult. So we turned to structured expert judgment. Well, we know that we often ask experts for their input, and this is a way of actually asking them to give us quantitative measures, and to do so in a way which preserves empirical control in the same way that you would for regular data in designing an experiment. We know that there are cognitive biases and things like this, so you need to control for these. So we use the IDEA protocol. Basically what we do, we send out background papers, we ask our experts to attend for a day, day and a half, whatever we need. We ask them the questions of interest. We also ask them calibration questions. So questions to which they don't know the answer, but we do, and for which they have to go through the same thinking process. So something that's quite close to their area of expertise. What we want to know is, out of our experts, who is good at estimating probabilities, because it's a hard thing to do. Then, when we've done that, everybody does it privately, so you don't actually get sort of like, I better put the same thing as the professor because otherwise they'll be cross with me, or they might not give me the job I want, or the promotion, whatever. So then you have a table, a round table discussion, but we've anonymized the actual results. So you can see everybody's results, and you can probably pick out yours, but you don't know who gave the others unless they choose to identify themselves. In that way, you can say, well, how could it be as high as this? Under what circumstances could it be as low as this? And then you can have some, well, I've seen this paper and so on. And so basically you share the information and the way in which you're thinking. And then you go for the second round. And the second round is the data you use, and you actually weight people by the performance on the calibration questions. So how informative are they? In other words, how narrow are their bands and how accurate are they? How often did the real value fall within their uncertainty bounds. So yes, the calibration questions are done by the same protocol and you use the second round. And these are some of the Brier score is a very common way of actually calculating the weights. These are the kinds of questions you ask. This is the kind of form that we gave them. What is the probability of observing good honeybee abundance given the environment is supportive, the weather is unusual, and the Varroa control is good? And we asked them first of all why it could be low, then what was the highest plausible bound, and then what is the best estimate. And the reason for that is to stop anchoring. And then we also capture some of the qualitative data. Why do you think that? So that you can actually do a qualitative analysis as well if you have skills in that area. So you have to agree on definitions before you answer the questions. What do you mean by good? What do you don't mean by good? I didn't know before we did this there's a Bees, Wasp and Ants Recording Society, and they put things on the database. Have to be a bit careful with that because it's much more prestigious to put an unusual one than a usual one. You might just sample in the same spaces as the same place, but you know, this is all we have. And also the Hoverfly Recording Society. The environment, we had a bit of a discussion about that and decided that was a paper that said a supportive environment is one where there's at least 1 hectare. No, that wasn't it. 15% semi-lateral land, that's it. They preferred this definition, so we changed the definition. So that's the protocol, we've done that. These are the kind of graphs that we see. So you can see that this expert, the round one is the black one. This expert was very much more optimistic in round 1 than in round 2. This particular expert had a very uncertain, and we had to ask them, is this your uncertainty, or is this you think the system is uncertain? It's important for us to understand that. And after the discussion, they were actually much more certain, and it was because they were actually an expert in hoverflies, and this was a question on honeybees. So we discretized the populations into honeybees, hoverflies, and other bees. And similarly, we had again somebody with a big uncertainty. We had a lot more variety here, and we discussed why could it be as high as that, why could it be as low as that. And then there's this one where almost nobody changed their mind between round 1 and round 2. So we have proposed a generic methodology for coherent inference over a network of probabilistic systems, and identified some plausible, useful network frameworks for using that. And we're beginning to demonstrate its usefulness for pollination and food poverty policy. Thank you.